Here we go. Okay, we're recording. So let's talk about old school division. This is something, I don't know what grade you guys do division. I'll probably find out when my son is in 3rd or 4th grade. He's in kindergarten now. But I'm guessing probably in 4th grade you guys do division. I don't know. But if you guys remember, old school division looks like this. You guys remember that process? And you have to figure out how many times 13 goes into 16, which is once. What do you guys do after that?
How many times does
Yeah. And then that becomes 35. You bring the 5 down. And that goes in how many times? Twice. You get 26. You get 9. You get remainder 9. Really what it is, it's 12 plus 9 out of 13. That's the same exact thing as 165 out of 13. So just so you know, it's not some sort of magical thing. It's the same exact thing. 12 remainder 9 is the same thing as this, right? Or 12 plus 9 13ths. Or if you want to do it as a mixed number, 12, 9 13ths. Of course, we use an improper fraction to get back. So 165 out of 13, but it's the same thing, right? Let's do it again. If I do again for example 2.
You have to do plus 9 13ths, or can you do 12 or 9 13ths?
You could do 12, 9 13. Yeah, as a mixed number. That's fine too. How many times is 17 go to 34? Twice. So you get 34. Now, fortunately, that is 0. But you still got to bring the 5 down. Now, it's a little tricky. You don't bring the 1 down yet.
0.
It's going to be 0. 17 goes to 0, 5 0 times. So you got to put a 0. It's one of those weird things with math when we do division. And that goes in 3 times perfectly. So the answer is 203. Okay. So that's division, right? Long division. We're going to be doing the same thing with polynomials. It's not the most fun thing to do. I'll try to make sure we do more synthetic division, which I think is an easier, more effective process. But synthetic division doesn't work all the time. I believe you guys did do this in algebra 2. I think it got kind of lost in the weeds 2 years ago when we were doing that crazy 4-week semester thing in the spring. God, we hope we never do that again. But let's do it for example 3 here. So here's how it's going to work. You can put x squared plus 2 on the outside. And you're going to put this on the inside. 8x5 plus 0x4 plus 0x3 plus 2x squared minus 3x plus 2.
Wait, what?
Okay. All right. Okay, yes, what? What's going on here? No, you do. Here's the reason why. What's the highest degree in the numerator? And then, of course, we're going all the way down to 2. Any term that's skipped over, no place for it. Not kidding. So 0x4 and 0x3 have to put a placeholder for this process to work. Same thing with synthetic division, which again is more effective. And if you guys forgot synthetic division, maybe I'll show it to you guys in a few minutes. But you do have to put a placeholder. So I know it's a pain. But that's what we do. Now, I promise I'm not going to give everyone this big on a test or homework quiz because I think that's kind of cruel. But I just want to show you the process. And again, I do think synthetic is a better way to go if you can do it. But this one, we can't do synthetic, and I'll explain why in a few minutes. So this is long division, right? So you have to focus on the leading terms. And you have to ask yourself, it's kind of the same thing. It's a parallel to what we just did in the previous 2 examples. What do you multiply to x squared to get to 8x5? What do you multiply to x squared? 8x to the 3rd, good. Excellent. And then you would multiply 8x third to x squared plus 2, right? So you get 8x5 plus 16x cubed.
Wait.
So what did I just do? I don't know either. No. I multiplied. Sorry, I glossed over that. So it's just like the same thing as before, right? Remember, whatever number you put up top, you have multiply as well as on the outside and bring it to here. And we have like 17 divided by 1 over 34, 100, whatever. And the 17 times 2 is 34 and divide it down. Same thing. When you multiply this by 8x cubed, what do you get? 8x5 plus 2 times 8 plus 8x cubed.
Oh, you have to do that.
Right. You got to do that. We're okay with this so far? We're good? Okay.
Now, this is the part that people will really mess up because I've graded these problems for so many years. Most people don't do this. I am an
OCD freak when it comes to parentheses. I do like, do you look at my Excel spreadsheets that I do for like other type of data stuff? I put like a zillion parentheses because I don't want my data to be messed up. I'm gonna encourage you guys to use parentheses often. So for some reason, there's an aversion to parentheses. I don't know why, but it really helps you because you realize that 8x5 has to be subtracted to 8x5, and this is not being added, it's being subtracted to 16x here, just like you did for normal long division.
But so why is the 8x equal to 5 on that?
Because it is 8x cubed times x squared. Because I try to find how many times this went into this.
Yeah.
So you have to make sure it's the same thing. Yeah, because, and again, you're multiplying all this, what's in green, you're multiplying x squared plus 2 with 8x cubed, which is 8x5. And so that's why there's an 8x5 down below. So that cancels. And this becomes negative 16x cubed. And then you bring down the plus 2x squared.
Why is it minus?
Just like the way long division works, like if I have 5 divided by, say, 2, 10, how many times 5 go into 21? And then you subtract. Same exact thing. If it helps, think of what's happening in normal long division numbers. It's a parallel to it. Now, how many times x squared go into negative 16x cubed? How many times does x squared go into negative 16x cubed? What do I multiply by?
16x.
Good. Excellent. Good. So you guys are getting it. So you get negative 16x cubed minus 32x.
I don't understand.
Go ahead.
The negative, like, how do you get negative?
What's 2 times negative 16?
Grade two?
There you go. Yeah, exactly. Yeah, you have to multiply everything, because this is the entire thing on the outside. You have to multiply everything, whatever you put up here.
And then you subtract again. In this case, I get 2x squared plus 32x. I'll bring down the plus 2. Now, we're almost done. Let me erase some stuff here because it's getting a little busy. 2x squared from up above. Right here. Right here. Oh, you're right. You are correct, Charlotte. I messed up. Good. You guys are getting it because you corrected me. Sorry about that. I forgot to bring down the negative 3x as well. My apologies. Thank you, Charlotte, for catching that. So it's plus 29x. You're correct. You got to bring down enough
To combine with what you have over here. You have to combine. I messed up. I forgot to bring it over here.
So you always start with like,
Yeah.
so like the x squared.
Right. Right. And then I'm going to put plus 2 afterwards. It is horrible. And then you get 2x squared plus 4, right? So I ran out of space. So let me
Is there another way to know this?
this particular problem, no, does not, unfortunately. So I ran out of space. Let me select it and move it. Hold on a sec. Oh, come on. Hold on. Almost. Let me just select it really quickly. There we go. Perfect. Okay. Then I have to do minus 2x squared plus 4. Which will be 29x minus 2.
Yeah.
And that's my remainder. So it becomes 29x minus 2 all over x squared plus 2. Yeah, this is a brutal long division problem.
That was horrible.
I don't get it.
That was actually horrible.
Okay, what don't you get?
How'd you get that?
Okay, so every single time I'm not doing anything unique with each step. Every single time I'm multiplying by this, right? What's 2 times 2x squared plus 2? 2x squared plus 4. And subtracting with what's remaining. When I subtract the two x squares cancel, I have 20x minus 2. Now, here's how you know you did this right. Because I did a lot of steps and I did make a mistake. Charlotte, think that's not a mistake of mine. Here's how I know this right. And by the way, something like this can show up on an SAT exam. It can.
Right.
No
Yeah,
way.
Not this bad. This is really bad. This isn't bad. But something similar, sure. I can show you some real tests that where I've seen this. What if you let x equal? What if you let x equal 1? What happens? You have 2 minus 3 plus 8 plus 2 over 1 plus 2. What's that going to be? That's going to be 9 over 3. 3. Okay. Now, what do we get as our answer? We got this as our answer, right? Go and plug in 1. If you let x equal 1, you should get 8 minus 16 plus 2 plus 27 over 3. You get negative 6 plus 9. Oh.
It's not 16.
Negative 8 plus 2 is negative 6. And then 27 over 3 is 9. You get 3 again.
That's not a coincidence. That's not a coincidence.
Because all you're doing is you're cosmetically changing that fraction. Granted, I think this fraction looks much nicer than all this junk I just did. And this junk that's highlighted in yellow looks really nasty. But you are going to need this skill. I'm going to tell you right now. When you move on to calculus, because I've taught calculus for nearly 2 decades, you're expected to know to do this. When you use, there's something called an integral. You guys heard of derivatives? Like maybe you have friends taking calculus. First semester, you do things called derivatives, which are like slopes of tangent lines, like rates of change. Second semester, you do integral calculus, where you're looking at it's the opposite of a derivative. You're looking at like total change, stuff like that. In order to do this calculus process called an integral, sometimes you're going to have to do long division in order to make the problem simpler work. So it's a skill set you will need. It's going to come back with a vengeance in a year from now. So I feel like at least I have to at least introduce and talk about it. I'm sure you guys will forget because you have other things going on. Summer's coming up. There's a lot of fun stuff. Proms this weekend, right? NBA playoffs. But I at least have to talk about it. That's at least my job to talk about it. So it's a nasty process, but it's a skill that you will need to use in calculus down the road. I'm not going to do example 4 because I think I tortured you guys enough. But actually, let me show you a way you could do example. Let me show you a workaround for example 4. So I am going to do it, but I'm going to show you a workaround. What can you factor up from the top? So it basically looks like this, right? No, just 5, right? We'll factor out 5, so it looks like this: negative x5 plus 1. Sorry, negative x5 minus 5.
Minus 1, right?
Minus 1, sorry, minus 1, right? And down below, you do this, right? What happens to the 5s? They cancel out. So really, what you have left is negative x5 minus 1 over x plus 1. We agree?
Hmm.
Okay. Instead of doing long division, we're going to do something called synthetic division. This is a much, much better process. Yeah. You can't, and here's the reason why. I'm glad. Great question. Probably one of the best questions I've heard in a few months. Great question. The reason why you cannot is because it has to be a linear expression. Yeah, it has to be a linear expression. There's a linear expression requirement. For example, 3, x squared plus 2. Is x squared plus 2 linear? It's not, right? It's quadratic. That's the reason why. So you have to have linear expression. Also, the leading coefficient has to be 1. So you have to force out a number from that. But after that, then it's pretty easy. Here's how it works, in case you guys forgot. So let me write it again one more time. You do. So this right here is like x5. This is like x4, x3, x squared, sorry, and a constant. That was a little loud. Okay. So here's how it works.
Because you have to put placeholders for all the other terms that get skipped. There's no X4, there's no X3, there's no X3, there's no X. X4, X2, X2, X. You have to skip them over.
But trust me, this goes by really fast. Does anyone remember how this works? Okay, that's fine. I love the honesty. You bring down a -1. You bring it down. The first. Good. Thank you, Claire. You multiply.
You get one. I said that if you put it underneath the zero.
Exactly. See, it's coming back. Then what do I do, Claire? Yes, good. Then you add it. And guess what? You rinse and repeat. Rinse and repeat.
One. Wait. You add one to what? What does she add one to?
It's right here.
To zero?
Yeah.
Okay.
And what's 0 plus 1? 1, right?
So then you just keep it negative one.
-1, add it.
Then what?
Wow. I love the enthusiasm. All right, here. I'm gonna do this. This is the beauty about doing on Zoom. I could undo. So are you okay still parked by half?
Yeah, I get that.
Okay. So that was 0 plus 1. Okay, what's -1 times 1? Boom. Then what's 0 plus -1? Boom. So it's -1 times -1. What's 0 plus 1? What's -1 times 1? What's 0 plus -1?
So you're multiplying it to the one.
Oh, oops, you're right. Yeah, -1. My bad.
You don't multiply it to that first negative.
No. No.
Negative one.
So what do all these numbers represent? They represent the coefficients of your answer. So it's going to be -x4 plus x cubed minus x squared plus x minus 1.
Wait, what happened to the next coefficient?
So what happens when you do the division?
Great question. That's a great question. You always go one less
Okay.
because you're doing division, right? So you go one less in the degree. Always go one less. Now, how do I know I did this right?
How do I know I did this right? Well, let me do a little verification. Let's do a little check here. Let x equal 1. If you let x equal 1, what does that become? That becomes -2 up top and 2 on the bottom, so you get -1, right? Now plug into here. Plug in -1. Sorry, plug in 1. -1 plus 1 minus 1 plus 1 minus 1, you get -1 again.
That's how I know I did this right. Because if I plug in a number into the original expression and a number into the answer, I get the same exact thing. This is really a simplification process. You're factoring out. You're actually factoring out as you're doing. Yeah, but
Okay, so you give us. How did division?
Right.
What? How do you want us to write our answer? Do you want to write it in the red?
The red. The black is just a check.
So you have to go a step further than that.
Yes, exactly. Right. So we're going to do more. We're going to do some more. I'll do synthetic because long division is kind of just painful.
Yeah, it sucks.
It sucks. It does suck. Okay, let's look at example 5. Let's try this again. -2. And by the way, you always put a number that makes the denominator equal to 0.
you don't. But what you're doing here, it's gonna make more sense next week. What you're doing is actually pulling out an x-intercept. Because you assume that x is the factor of it, and negative is an x-intercept. That's what you're doing. No, I agree. You never want the bond to be 0, but that's just the way the process works.
Now, what I'm going to put on the inside? What's the first one we're going to put, guys? What's my highest degree? X of 4, so I'm going to put a 1. My height, so if you have to put this in descending order, x4 plus 5x cubed. There's no x squared, right? There's a -x and -2. So that's why I put a 1, because that's the leading coefficient. What's the next coefficient? What's the next coefficient?
Wait, why do you put a 1?
Because you have to find the highest exponent. The highest exponent is x4. And what's the coefficient of x4?
1.
Exactly. And what's the next highest coefficient?
3.
Well, sorry, the next highest degree, x cubed. Yes, x cubed. What's the coefficient for that? 5, exactly.
Then minus 2.
And then -1 and -2,
Why am I, oh,
because you have negative x, exactly. All right, and then Claire, you want to do the honors? Right. Look at you, you're a synthetic division machine. All right.
go back.
No, I'm just kidding. She just did arithmetic, that's all. She did second grade math. Sorry. Okay, you brought the 1 down, right? I'm having fun with this. This is fun. All right, what's -2 times 1? I'm sorry, I'm being sassy. What's 5 plus -2?
It's 3.
What's -2 times 3?
Divide -2 to everything.
Exactly. It's
Okay.
rinse, that's what I said, when I said rinse and repeat, I really meant. You rinse, like,
And then you would do.
this whole process of rinsing and repeating.
-2 to 12.
No, you bring down the negative 6, right?
Okay, so you get this, right?
Yeah, and then
12.
12, and then
12
11.
minus
Boom. There you go. So the final answer will be written like this. Yeah, you always go 1 degree less.
That a remainder?
It is remainder. So you have x cubed minus 6x plus 11 minus 24 all over x plus 2. And trust me, when you guys do move on to calculus, you're gonna have to
When you're doing this calculus process, the problem with this, you need to have it expressed like this, you can easily do the calculus process that I talked about
a few minutes ago called integration. But so in example 6, you must use. I'm not going to do it because I just don't want to.
So like one of
So- You know, given how vast this unit is, I'm 99.9% sure I don't want to test long division.
Yes.
I think I'll just do synthetic. I will make a pitch to avoid long division because there's so much stuff here.
he likes to be part of the
We give the same test, just so you know. I mean, our tests, right? But then I did a harder problem in that that piecewise function. I had you guys find the x-intercept. She did not. And also, our grades, our averages are pretty much the same. So it's like, yeah. Anyway. I mean, our class had more transitions. I was gone for 4 months.
Yeah.
That might be different, but anyway. You know, I think you guys get the point here. I'm just gonna set this one up.
Yeah, like what about this one?
Okay, so this one, because it's 2x minus 3, what you do is you write it like this. You put 2 on the outside, you put x minus 3 halves. And then what you do is you divide each of these by 2. Because it's looking like this right now, right? 2x4 minus 9x cubed plus 21x squared. I skipped example 6. I didn't feel like doing it. So what I just wrote, does that make sense?
No.
Okay,
So I factored out 2 from this. Even though the reason I was by 2, I forced it out. If I force out the 2, then what does -3 become? -3 or 2. Because what happens if I put the 2 back in? Do I get back to this? I do, right? That's the whole point back here. You gotta guarantee you can distribute, get back to the end original. So now the denominator is like this. So I broke off the fraction like this, having all the numerator stuff divided by 2, but also multiply by 1 over x minus 3 halves. It's the same thing. Because what happens if I bring these 2 fractions back together? Same thing, exactly.
So then what you would do, you'll see why. You'll see why. Because then you'll have x4 minus 9 halves x3 plus 21 halves x squared.
How does that make it easier?
Just guys, be patient. Just be patient. I'm gonna tell you in a sec. You guys are funny. All right. Kind of like my 6-year-old's like, why are we doing this? So
Now, you can do synthetic division. Because what's the coefficient of my denominator? What's the coefficient of my answer now? 1. So now you can do synthetic division.
Because you have to have the you have to have the coefficient of the denominator be 1. So now, if I erase all this junk here, I need more space. Come on. Here we go. So now, when I do the synthetic division, it looks like this. We're not going to do it because you guys get the point of how to do it. But now you have this 1, -9 halves, 21 halves, -13, 6, and -3 halves. And then you do the synthetic division after that.
But we're supposed to do that with fraction.
Yes.
I'm not going to do it because it's just a little too nasty, but that's what you have to do.
Would that be on the?
No, I think more like, I think example 5 was a perfect problem. I agree. That was a perfect problem. So, but I just need to show you varieties because I don't want any. The bottom line is this: I don't want misconceptions. I don't want you to just walk out of and think, "Oh, you can always just synthetic division where you want." No, that you can't. You have to alter sometimes the problem to get it to work. I feel at least it's my duty to kind of at least be forthright about it, not leave it, let you guys walk away with misconceptions. So the bottom line is this: if you have a polynomial divided by x minus a, then you do a with all that junk. That's how it works. That's the process. All right, almost done here. Well, kind of. I'll be done pretty soon. All right, so here's another thing we need to know. It's called something called the factor theorem. X minus a is a factor of a polynomial as long as this is true. As long as f of a equals 0. Because what this means is that y equals 0. What this means is that a is an x-intercept. Since f of a equals 0. That's what it means.
Because f of whatever is y, right? If y is 0, you're on the x-axis. It's the x-intercept.
So let's do example 8, just so you see how this works. You have to evaluate f of -2. Okay. You guys know how to do this, right? You guys are comfortable with this? We're good so far? Yeah? Okay. Let's work it out. What do you guys got? 3 times what? Guys, let's go. 2 times.
Oh, -2 is -2.
That's
Wouldn't that be
16.
16?
PEMDAS, good. We're okay? 48 minus 8. Let me back up a little bit. We're okay? No, we're not okay? Okay. Too easy? Oh yeah, it is too easy. I'll make it even easier. I'll give you something similar. Hold on a second, let me finish it off. So you get 17, right, as your final answer? All right. So here's the issue with this process. You can make an error pretty easily, right? Because a lot of negatives, a lot of subtraction. You could have done this if you wanted to. And you could have made an error with this process also, but you could also have done this. You could do synthetic division for this problem.
How do you do that?
You'll see. Okay, let's do it. So you put -2 on the outside, and you put all the coefficients on this side. Drop the 3 down, and go ahead. What's the next step? Look at that. That's not a coincidence.
You could use synthetic, it's called synthetic substitution, actually. You can do the synthetic process to evaluate a function. You can do it for any polynomial. Works all the time. That's called the remainder theorem. What I just did right now is called the remainder theorem.
So this works out very, very nice. So the remainder theorem states that when you divide a polynomial by x minus a, it's the same thing as plugging a into the function. It's the same exact thing. So let me write that in kind of layman's term. When you divide a polynomial by x minus a, you get the same thing. The remainder is the same thing as plugging in x equals a into the function. It's the same thing. Hold on. There we go. So when you, gosh, that's hard to read. Let me erase. That's awesome. Here we go. Select. Here we go. Same exact thing. So if you got a zero remainder, like for example, coming back up here again, remember we had negative x5 minus 1 over x plus 1. Yellow is not a good color, but and remember we did all this junk here, x4, x3, x2, x, and negative 1. If you do synthetic division here again, you would get I think 0, because you'd have negative 1, 1, 1, negative 1, negative 1, 1, 1, negative 1, 1, 1, 0. Here's the thing, because you get a remainder of 0, then x plus 1 is a factor. Because it means it went cleanly, right?
Just divide it cleanly, but everything's divided cleanly, you get zero remainder, right? So this means the x plus is a factor. That's called the factor theorem.
And we're going to drive this point home a lot next week. But I care more about the mechanics of the stuff. All right, next up. Examples 9 and 10 I'm going to keep kind of short because this can get very painful. Examples 11 and 12 I like more because those are more relevant. But when you're asked to write a polynomial function that has the following zeros, honestly, just do this. It's really just one step. Done. That's it.
Now, could I ask you to FOIL? I can. Will I? No.
Wait, is it negative one?
Does that make you say? Yeah, but it's x plus half. You always add the opposite. You want, when you plug negative 1 half in, you want 0 to be 1. Like try plugging negative 3 back and I want y to be 0. So you write in factor form, right? That's not hard. Will I ask you to FOIL again? No, because I think that's useless. You guys have done a lot of FOILing in middle school and algebra too. I don't need to have you guys FOIL it. It's totally pointless process. You could do it, but why?
It's good enough. Like same thing here.
You just feel like it's actually squared.
No, because you only have one negative 6. They're all different zeros. If there are multiple zeros, yeah, sure, go ahead and do that. But none of the zeros are repeated, right? They're all unique. So you have to have unique factors, right? Because all these are unique zeros. These have to be unique factors. That's it, done. That's all. I don't want you to FOIL. So don't FOIL. I think it's just this tool useless. All right, this I do care about. And this I have seen show up on ACT, not SAT necessarily, but I've seen it show up on ACT, this type of situation. So you're told that this is 0. So here's what you're going to do. That means that what this means sorry, let me type that up. That's just stupid. Come on, let's redo this. All right. What this means is that x plus 1 is a factor of f of x. That ladies and gentlemen, is the factor theorem. That's the factor theorem. So what you're going to do is this. You're going to actually divide it out. Synthetic, please. So divide f of x by x plus 1. So that's what we're going to do. You put -1 here, 15, 14, -3, and -2. If you want to use long division, go ahead. I think you'd be crazy if you did. You'd like to be crazy, that's good. But don't. So yeah. So you get 15, -15, -1, 1, -2, 2. It should come out cleanly. If it doesn't, you made a mistake. It should come out cleanly. So what does this represent now? This is what, 15? Okay, if I set this equal to 0, I could factor this, by the way. You guys remember the little diamond thing?
So it's like -30 and negative.
Yeah, or -6 and 5. But yeah, right. What's that going to be? I'm trying to do this in my head. -6 times 5 is -30, and -6 plus 5 is -1. You will get -2, but you're going to write like this first.
Oh, right, you have to prove it.
Thank you. Yes. See, it's all coming back. It's all coming back, right? Stuff from last year and 3 years ago. Yeah, so if you do factor by grouping, you should get, what do you get here? So hard in your head. I think final answer is 3x plus 1 times 5x minus 2. Yeah, because you factor a 5 from the first group. Sorry, you factor a 3 from the first group and nothing out of the second group. So yeah. So the final answers are -1/3 and 2/5. If you go to Desmos, you get the same thing. Yeah, -1/3 and 2/5. Yeah, that's all. Let's try this one more time, and then I'm done. You guys can start the homework. Let's look at this one more time. So I'm going to do this. -4, 2, 7, -5, -4. So, and by the way, you can't do factor by grouping for this one, so you had to be given one of these zeros here. Bring down the 2, -8, -1, 4, -1, 4, 0. Does that make sense what I just did?
I don't have to, sorry. But people think that's good. So you put -4 on the outside, put this in, bring down 2, blah, 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 just go through it. That factor is not so bad. That should be, I think, 2x.
-1? No, 2x plus 1, x minus 1. I think, does that make sense? Yeah. So you get -1/2 and 1. By the way, how can you use technology to verify this? Desmos, exactly. Just plot it in the Desmos is lovely. Just check your work that way. Of course, you can't do it on a test. You can use a graphic calculator, you can do that and graph it and see what it costs the x-axis, same thing. That's a graphical algebraic connection, which is huge. And numerically, we know this makes sense because if you plug these numbers back in, you get 0, right? If you plug in 1 back into the function, what do you get when you plug 1 in? 2 plus 7 is 9. -5, -4 is -9. 9 minus 9 is 0. I know this makes sense. So numerically it makes sense. Algebraic, I should have did it. And graphically, they cross the x-axis those places. Oh. Oh boy. How about just number 4? Just one. Just do it once. Skip 1 through 3. Just do number 4. So let me update Schoology really quickly. At the very least, you guys should try it. That means you can skip numbers 1 through 3. There we go. Okay, homework check-in we'll do in a few minutes. And hold on, let me stop recording.